Imagine that you are an astronomer. You observe a distant galaxy, record data, build graphs, and suddenly, a flash, supernova. One of the most powerful events in the universe is when a massive star ends its life in a grandiose explosion, ejecting matter and energy into space, eclipsing its entire galaxy for a short time. You document the event, publish an article, check your catalog. The star died. Curtain. But a few months pass, maybe a year, maybe 5 years, and you check this area of the sky again. Just a routine. And what do you see? The same star explodes again, with the same brightness, with the same characteristics. The supernova repeated. Your brain refuses to accept it because it's impossible. Supernovae do not repeat themselves. When a star explodes as a supernova, it either turns into a neutron star, a black hole, or completely flies apart. This is a one-time show. The ticket is valid for one session only. But here is the same flash in front of you on the monitor screen again. Another explosion. Again a supernova. Zombie star. It exploded, was supposed to die, but instead resurrected and exploded again. Welcome to one of the strangest and most frightening phenomena in modern astronomy, the world of recurring supernovae. Now we're going to dive into a story that sounds like science fiction, but it's real science. We're going to talk about stars that refuse to die, explosions that repeat themselves against all the laws of physics, mechanisms so extreme that they literally tear stars apart, but don't kill them completely. We'll break down real-world observations, delve into the physics of these processes, and by the end of this journey, you'll understand why astronomers call these objects a nightmare, why they upend our understanding of stellar evolution, and what they can tell us about the most extreme conditions in the universe. Let's start with the basics, because to understand how crazy repeating supernovae are, you first need to understand what an ordinary supernova is and why it should be the final act in the life of a star. A star is essentially a giant fusion reactor, where gravity tries to compress matter to a point, and the pressure from thermonuclear reactions in the core resists this compression. This is a war that lasts for millions or billions of years. And as long as fusion is going on in the core, the star is in balance. Hydrogen turns into helium, energy is released, and pressure keeps gravity in check. But sooner or later, the fuel runs out. For massive stars with a mass greater than about 8 solar masses, this is the beginning of the end. When the hydrogen in the core runs out, the star moves on to fuse helium into carbon and oxygen. Then carbon into neon and magnesium, then neon into oxygen and magnesium, oxygen to silicon and sulfur, and finally silicon into iron. Iron is a problem. Iron is a dead end. All the elements before iron release energy when they are synthesized. But the synthesis of iron into heavier elements requires energy, not releases it. Therefore, when an iron core accumulates in the center of a massive star, thermonuclear fusion stops. There is no longer any pressure that resists gravity, and the core begins to collapse. In a fraction of a second, an iron core the size of the Earth shrinks to the size of a city. Electrons are pressed into protons, forming neutrons, and neutrinos are released. When the density reaches that of the atomic nucleus, the neutrons begin to resist further compression through the quantum pressure of degeneracy. The collapse stops so abruptly that it generates a shock wave that rushes back outward through the star, tearing it apart. This is a supernova of the second type, the collapse of the core. An explosion of such power that in a few seconds it releases energy comparable to the energy that the sun will radiate in its entire 10 billionth life. That leaves either a neutron star, an object so dense that a teaspoon of its material would weigh 1 billion tons, Or if the mass of the core is too large, even neutron pressure cannot stop the collapse, and a black hole is formed. This is a one-time event. A star cannot explode twice, because after the explosion either a compact object remains, a neutron star or a black hole, or the star is completely destroyed. No star, no re-explosion. This is logic, this is physics, this is what is taught at universities. But the universe likes to throw surprises at us, and sometimes these surprises are so strange that they force us to rewrite textbooks. The first hints that something was wrong did not appear immediately. The history of repeating supernovae began with observations that at first seemed to be just strange anomalies. Astronomers recorded supernovae that behaved unusually. Some of them were too bright, some are too dim, some showed strange spectra. But the real breakthrough came with the development of automated sky surveys. When telescopes began to regularly scan the same regions of space night after night, year after year, astronomers were able to track long-term changes. And it was then that cases began to emerge that could not be explained within the framework of the traditional model. One of the most well-known and well-studied examples is an object called IPTF-14HLS, a supernova discovered in 2014 by the Automatic Sky Survey of the Intermediate Palomar Transient Factory. At first, it seemed to be an ordinary Type II supernova, a bright flash, a characteristic spectrum with hydrogen lines. Astronomers cataloged it and continued their observations, as they usually do with supernovae, to trace the light curve, how brightness changes over time. A normal supernova reaches a peak of brightness and then gradually dims over a few months. But the IPTF-14HLS did something completely different. She didn't just fade. It became brighter, then faded, then brighter again, oscillated. And this lasted not weeks, but months. For more than 600 days, astronomers have observed this object pulsating in brightness, showing at least 5 separate peaks. When the researchers began digging through the archival data, they discovered an even stranger thing. In photographs taken in 1954, 60 years ago, a flash was recorded in the same place in the sky. The same star exploded in 1954, and then again in 2014. 60 years between the explosions. One object, 2 supernovae. This was impossible, but it was recorded on photographic plates and modern CCD sensors. Zombie star. When the article on IPTF-14HLS was published, the astronomical community was shocked. Because it's not just an anomaly in the data. This is not a measurement error. It's a real physical object that behaves in a way that contradicts everything we've ever known about supernovae. Theoretical research began. What mechanism can cause a star to explode multiple times? How can a star survive its own supernova and retain enough mass and structure to explode again? One of the leading hypotheses is related to a phenomenon called pulsated paranstable supernovae. This is one of the most extreme phenomena in stellar physics, and to understand it, we need to talk about what happens in the interiors of very massive stars at very high temperatures. When the mass of a star exceeds about 100 solar masses, and the temperature in the core rises above a certain threshold, about 2 billion kelvins, a process begins that sounds like something out of the realm of science fiction, but it's pure physics. At these temperatures, photons, particles of light, have such high energy that they can spontaneously transform into particle-antiparticle pairs, specifically an electron and a positron. This is called vaporization, and it poses a fundamental problem for the star. Up to this point, the pressure in the star's core has been maintained mainly by the pressure of radiation. Photons flying in all directions create a pressure that resists gravity. But when photons begin to turn into electron-positron pairs, they disappear from the radiation pool. Fewer photons mean less radiation pressure. It's as if a support was pulled out from under a star. The pressure drops, gravity begins to take over, the core begins to shrink. Compression increases the temperature. An increase in temperature accelerates thermonuclear reactions. Fusion goes faster and faster, and a huge amount of energy is released. But this energy does not save the star, it tears it apart. The explosion is so powerful that it dumps the outer layers of the star, perhaps tens of solar masses of material, into space at speeds of thousands of kilometers per second. It looks like a supernova. It is a bright flash visible across the galaxy. But here's the key point. The core of a star can survive this explosion. If a star is massive enough, then even after it has shed a huge amount of mass, there is a core in the center that is still massive enough, still hot enough to continue nuclear fusion. The star is wounded, but not killed, continues to live. And this is what happens next. The core cools after the explosion, the pressure stabilizes, and the star returns to some semblance of equilibrium. But after a while, maybe years, maybe decades, the temperature in the core rises again, vaporization starts again, the pressure drops again, and the whole cycle repeats. Another explosion, another pulsation. A star can go through several such cycles, exploding over and over again, each time shedding some of its mass, until either the mass is low enough that the star stabilizes, or the core finally collapses into a black hole. These are pulsating paranstable supernovae, and they explain how a star can explode repeatedly. Each explosion is not the final death of a star, but a pulsation, the convulsion of a dying giant who desperately tries to balance the internal forces but cannot. It's like agony, stretched out over years or decades, where each convulsion is powerful enough to outshine the galaxy. Theoretical models of pulsating paranstable supernovae predict certain observed characteristics. Multiple flashes of brightness. Outbreak intervals range from months to decades. Large total energy released for all flares. Spectra showing hydrogen because the outer layers of the star are still rich in hydrogen. And when astronomers compared these predictions with observations from IPTF-14HLS, the coincidence was striking. There are multiple peaks in brightness. There are intervals in years and decades between explosions. There are spectra with hydrogen. Estimates of the mass of the parent star from models yielded a value of the order of 100 or more solar masses, precisely in the range where paranstable processes should dominate. But IPTF-14HLS wasn't the only one. As astronomers began to specifically search for such objects, other cases began to surface. SN 2009 IP, for example, is another strange recurring supernova. It was discovered in 2009, and at first it seemed to be an ordinary transient. But then in 2012 it flared up again and much brighter. Was it the same star exploding again? Or was it a series of eruptions leading up to the final explosion? The debate continues, but one thing is clear: this object does not fit into the standard model of supernovae. There is also a whole class of objects called superluminous supernovae, some of which show signs of multiple components in their light curves, hinting at multiple energetic events. These objects are so bright that they can outshine entire galaxies, and some of them may be related to paranstable processes or other exotic mechanisms. Now, let's delve into physics a little more, because paranstable supernovae are only one possible model. There are other mechanisms that can lead to repeated explosions. One of them is related to accretion to compact objects in binary systems. Imagine a binary star system where one of the stars has already gone supernova and turned into a neutron star or white dwarf, and the other star is a massive giant or supergiant. The compact object gradually pulls matter from the companion. Matter falls to the surface of a white dwarf or neutron star and accumulates. When the mass of the accumulated matter reaches a critical value, thermonuclear flares can occur on the surface. For white dwarfs, these are new and recurring novels. The hydrogen on the surface of the white dwarf is compressed and heated to temperatures at which uncontrolled thermonuclear fusion begins. The explosion dumps the accumulated material into space. The white dwarf remains unharmed, and the process can be repeated. But it's not exactly a supernova in the classical sense. It's a less energetic event. However, if the white dwarf continues to gain mass and approaches the Chandrasekhar limit, about 1.4 solar masses, then a true Type 1 supernova can occur. The carbon and oxygen in the white dwarf ignite in a thermonuclear detonation, completely destroying the star. This is no longer a repeatable event. But there are even more exotic scenarios. For example, if you have a very massive star with strong stellar winds or pulsations, it can periodically shed large shells of material. When the inner layers of the star finally collapse and generate a supernova shock wave, this wave can collide with previously ejected shells, and the interaction can create multiple peaks in brightness. These are not multiple explosions in the strict sense, but a single explosion interacting with multiple shells, but observantly it may look like a repeating supernova. It is also worth mentioning the tidal destruction of stars by black holes. When a star passes too close to the supermassive black hole at the center of a galaxy, tidal forces tear it apart. Half of the star's matter flies away into space, half falls into the black hole, creating a bright flash of radiation. If the star's orbit is such that it passes close to the black hole repeatedly, each flyby can create a flare. It's a recurring event, though not exactly a supernova. But observantly, such events can be very bright and repeat at regular intervals determined by the orbital period. Let's return to paranstable supernovae, because they are especially interesting from the point of view of extreme physics. Stars that experience these processes are at the very upper edge of the mass distribution of stars. These are the rarest of the rare. A typical galaxy the size of the Milky Way may have only a few dozen or hundreds of such supermassive stars in the entire history of the galaxy. Why so few? Because the formation of stars with a mass greater than 100 solar masses requires special conditions. Very dense star-forming regions with a lot of gas and low metallicity are needed. Metallicity is an astronomical term for the content of elements heavier than hydrogen and helium. In the early universe, just after the Big Bang, metallicity was virtually zero because heavy elements had not yet been synthesized by stars. The first stars, the so-called population 3, formed from primordial gas and could reach enormous masses, hundreds or even thousands of solar masses. Such stars would be ideal candidates for paranstable supernovae. But we can't observe the stars of population 3 directly. They are too far away and have existed for too long. However, we can see their legacy in the chemical composition of old stars and in theoretical predictions about how they should have exploded. Modern stars have a higher metallicity because they form from gas enriched by the explosion products of previous generations of stars. The high metallicity amplifies stellar winds, streams of charged particles that escape from the star. Strong winds carry away the mass of the star before it even has time to reach critical temperatures for vaporization. Therefore, supermassive stars in the modern universe rarely survive to the stage of paranstable processes. But there are exceptions. In regions of low metallicity, such as some dwarf galaxies or in special regions of large galaxies, stars with enough mass for parinstability can form. IPTF-14HLS was probably just such a star. Analysis of its host galaxy showed a relatively low metallicity. This is consistent with the idea that the parent star was very massive and formed under conditions favorable for maintaining high mass. Even so, seeing such a star in the modern universe is good luck. We literally caught the rarest phenomenon at the moment of its manifestation. Let's talk about what happens during the parent-stable supernova explosion itself, because the details of the process are mind-blowing. When vaporization begins, it does not occur instantly throughout the nucleus. There is a critical temperature about 2 billion kelvins, at which the effect becomes significant. As the core shrinks, the temperature rises unevenly. The central regions heat up faster. Therefore, the vaporization is first started in the center, creating a local pressure drop. The central layers begin to collapse, heat up even more, and thermonuclear reactions accelerate. A thermonuclear combustion wave occurs, which begins to spread outward. The speed of this wave depends on the composition of the substance and the conditions. In some cases, combustion can be subsonic slow, propagating due to thermal conduction. In other cases, it can turn into a detonation, a supersonic shock wave, after which the substance instantly ignites. The detonation releases a huge amount of energy in a fraction of a second. This energy creates pressure that tears the star apart from the inside. But here's an interesting point. The energy released in a parent-stable pulsation may not be enough to completely destroy the star, but enough to throw off the outer layers. It depends on the mass of the star and how deep the vaporization has penetrated into the core. If the star is in the range of about 100 to 135 solar masses, then the pulsations can be mild enough for the core to survive. The star experiences a series of explosions, gradually losing mass. But if the mass is higher, in the range of 135 to 250 solar masses, then the energy can be so great that the entire star is completely disintegrated in one catastrophic explosion, which is called a parent-stable supernova with no remainder. No neutron star, no black hole, just an expanding cloud of matter. For stars with masses above 250 solar masses, vaporization is so intense that the star collapses directly into a black hole without exploding. This is called a direct collapse. The star simply disappears without leaving a bright flash. There may be faint radiation from accreting matter, but not a supernova in the classical sense. Now think about what information these repeated explosions carry. Each flash is a window into the bowels of the star. By analyzing the spectra, we can determine which elements are present in the discarded matter. Hydrogen, helium, carbon, oxygen, neon, magnesium. The composition changes depending on which layers of the star were ejected. If the first flare shows a hydrogen-rich spectrum, it means that the hydrogen envelope has been ejected. If subsequent flares show more helium or carbon, it suggests that we are seeing deeper layers of the star. The light curve, the change in brightness over time, also provides information. The shape of the light curve depends on the mass of the ejected material, its velocity, and how it interacts with the environment. If the ejected material collides with previously ejected shells, the collision creates a shock wave that heats the gas and causes it to glow brightly. This can create additional peaks in the light curve. Therefore, by observing multiple flares and analyzing their characteristics, astronomers can reconstruct the history of the star, how many times it exploded, how much mass it lost, how quickly the matter flies away. For IPTF 14HLS, the analysis showed that the star had shed at least a few dozen solar masses of material during all the observed explosions. The ejection velocities were on the order of several thousand kilometers per second. The energy of each explosion was on the order of 10^51 ergs, roughly the energy of a typical Type II supernova. but this was repeated several times. The total energy released during all the events was enormous, far exceeding a single supernova. It is also interesting to think about what happens to the material dumped in these explosions. It scatters into the surrounding space, mixes with the interstellar medium, and creates an expanding shell of gas. Over time, this shell cools, recombines, and can begin to form molecules and dust. Heavy elements synthesized in the star are distributed throughout the galaxy, enriching the interstellar gas. Supermassive stars and their explosions are one of the main sources of heavy elements in the early universe. Without them, there would be no carbon, oxygen, iron elements necessary for planets and life. But let's get back to another aspect of recurring supernovae: their impact on our understanding of cosmology and astronomical distances. Type 1 supernovae, especially subtype Ia, are used as standard candles for measuring distances in the universe. The idea is that all type Ia supernovae have roughly the same luminosity at peak brightness because they come from white dwarfs that have reached the same critical mass limit. By knowing absolute luminosity and measuring the observed brightness, it is possible to calculate distance. It was with the help of type Ia supernovae that the accelerated expansion of the universe and dark energy were discovered. But if there are supernovae that explode repeatedly and have non-standard luminosities, that creates a problem. How to distinguish an ordinary supernova from a repeating one? If an astronomer mistakes a repeating supernova for an ordinary one and uses it to measure distance, the error can be significant. Fortunately, repeating supernovae so far seem rare enough not to pollute the samples for cosmological measurements. But as surveys of the sky become deeper and more sensitive, we will detect more such objects, and it is important to learn how to identify them and classify them correctly. Speaking of future observations, it is worth mentioning a new generation of telescopes and surveys that will revolutionize the study of transient astronomical events. The Vera Rubin Observatory Project, formerly known as LSST, will scan the entire accessible southern sky every few nights with unprecedented sensitivity. This means that we will detect transients at very early stages, track their evolution in real time, and identify rare and unusual events. If recurring supernovae are really as rare as we think, then only such powerful surveys can accumulate enough statistics to study them. Also, space telescopes operating in different spectral ranges will provide new information. X-ray observations can show shock waves from explosions interacting with the environment. Infrared observations can reveal dust forming in the cooling shells of the ejected material. Radio observations can track relativistic electrons and magnetic fields. By combining data from different ranges, we get a multidimensional picture of what is happening. Now let's talk about another type of repeating explosion that isn't technically a supernova, but is often mentioned in the same context: repeating fast radio bursts. These are mysterious bursts of radio emission lasting milliseconds, coming from distant galaxies. Most fast radio bursts are observed only once, but there are cases when they are repeated. The same source produces multiple bursts. The nature of these bursts is still not fully understood, but the leading hypothesis links them to magnetars, a type of neutron star with extremely strong magnetic fields. Magnetars themselves are products of supernovae. When a massive star collapses, a neutron star can form with a magnetic field trillions of times stronger than Earth's. Such fields are unstable and can be reconfigured in events called stellar earthquakes or magnetic reconnections, releasing huge amounts of energy in the form of X-rays and radio emissions. If a magnetar produces repeated radio bursts, these are also a kind of repeated explosions, although much less energetic than supernovae. Interestingly, some fast radio bursts have been localized in regions of active star formation in their host galaxies, which is consistent with the idea that the sources are young, perhaps newly formed magnetars. If that's the case, then we're seeing the effects of supernovae neutron stars still showing violent activity years or decades after their birth. This is another example of how star explosions are not just one-off events, but the beginning of a long and complex story. Returning to parent-stable processes, there is another aspect that is worth discussing: the role of the rotation of the star. Massive stars often rotate rapidly, especially if they formed from rotating gas clouds or are in angular transfer binary systems. Rotation affects the structure of the star. The centrifugal force opposes gravity in the equatorial regions, making the star oblate. This changes the temperature and pressure distribution inside. In some cases, rotation can delay the onset of pair instability because centrifugal force provides additional support against gravitational collapse. In other cases, rotation can speed up processes, leading to more dramatic explosions. Rapidly rotating massive stars can also generate powerful magnetic fields through a dynamo. These fields can affect the transport of angular momentum and energy, mass loss through stellar winds, and even the shape of the explosion. If the star rotates very quickly and collapses, it can form an accretion disk around a neutron star or black hole, and the energy released during accretion can be directed into relativistic jets along the axis of rotation. This could lead to a gamma ray burst, the brightest type of electromagnetic event in the universe. Some gamma ray bursts are associated with supernovae, and it is possible that repeating supernovae can also produce multiple gamma ray bursts, although such cases have not yet been observed. Now let's talk about how repeated supernovae affect the environment. When a star explodes, the ejected material flies apart at speeds of thousands of kilometers per second, colliding with interstellar gas, creating shock waves. These shock waves compress the gas, heat it to millions of degrees, and accelerate the charged particles to relativistic energies. Accelerated particles, cosmic rays, scatter throughout the galaxy, penetrate the interstellar medium, and affect the chemistry and physics of gas. Cosmic rays play an important role in regulating star formation. They heat the gas, preventing it from collapsing into new stars. They also ionize molecules, affecting chemical reactions. If a star explodes repeatedly, each explosion creates a new shock wave, a new batch of cosmic rays. Multiple explosions from a single source can create a complex structure of nested shells of matter expanding at different speeds. Collisions between these shells can create additional shock waves, amplifying the acceleration of the particles. As a result, the area around a repeating supernova could become a powerful source of cosmic rays and high-energy radiation. This has implications for galactic ecology. If there are many repeating supernovae in a galaxy, they can significantly affect the distribution of gas, its temperature, and turbulence. They can create hot bubbles of gas that expand and erupt from the galactic disk into the halo. This can regulate the rate of star formation in the galaxy, influencing its evolution. In the early universe, when supermassive stars were more common, such effects could have been particularly important. Let's also think about what observing repeating supernovae tells us about the limits of stellar mass. Is there an upper limit to the mass of a star? Theoretical models suggest that stars cannot be arbitrarily massive. At very high masses, the pressure of radiation from fusion reactions in the core becomes so strong that it can tear apart a star before it even has a chance to form. This is called the Eddington limit. For ordinary matter and normal conditions, the limit is a few hundred solar masses. But there are nuances. In conditions of low metallicity with weak stellar winds, stars can hold more mass. In conditions of high gas density, as in the centers of massive star clusters, accretion can last longer. The observed repeating supernovae, if they are indeed pair-unstable, give us experimental confirmation that stars with a mass of 100 solar masses or more exist. This is important information for the theory of star formation and stellar evolution. It tells us that under certain conditions, nature can create these extreme objects. Another intriguing question is whether repeating supernovae could be associated with the formation of intermediate black holes. Intermediate black holes are a hypothetical class of black holes with masses ranging from hundreds to tens of thousands of solar masses, intermediate between stellar black holes and supermassive black holes at the centers of galaxies. Their origin is unclear, but one idea is that they may form from supermassive stars or through successive mergers of stars in dense star clusters. If a supermassive star goes through a series of pair-unstable pulsations, it gradually loses mass. If the final mass of the core after all the pulsations is still large enough, the collapse could create an intermediate mass black hole. Alternatively, if multiple supermassive stars form close together and interact, their explosions and remnants can merge to create more massive objects. The speculative but recurring supernovae could be part of the puzzle. Now let's talk about observational challenges. Detecting and studying repeating supernovae is incredibly difficult. Firstly, they are rare. A galaxy the size of the Milky Way may have one such supernova per century or even less. Second, to confirm that a supernova repeats, you need to observe it over a long period of time, months, years, decades. This requires long-term surveys with constant sky coverage. Third, it is necessary to distinguish a truly repeating supernova from other phenomena that can mimic multiple outbursts, such as interactions with dense circumstellar envelopes or novae in binary systems. To do this, astronomers use a combination of methods. Spectroscopy is the analysis of the radiation spectrum, which allows you to determine the chemical composition, temperature, and velocity of a substance. The spectra of repeating pair-unstable supernovae should show hydrogen-rich lines because the outer layers of the star are still present. Photometry, the measurement of brightness in different colors, produces light curves that can be compared to theoretical models. Multiband photometry shows how the spectral distribution of energy changes over time, which provides information about the temperature and size of the emitting region. The localization of the source is also important. Determining the exact position in the sky and identifying the host galaxy provides additional context. What type of galaxy? What is the metallicity in this area? Are there signs of recent star formation? All this data helps to build a complete picture. Interestingly, some astronomers have begun systematically looking for signs of previous explosions in archival data for known supernovae. The idea is that if a supernova is repeated, then there could have been earlier outbursts recorded on old photographic plates or in archives of automated surveys. Such archaeological excavations in the data have already yielded results, as in the case of IPTF-14 HLS, where an outburst in 1954 was discovered in the archives. As historical astronomical archives are digitized, we can expect more such discoveries. Now let's talk about the theoretical modeling of repeating supernovae. This is one of the most difficult problems in computational astrophysics. To simulate the full life cycle of a supermassive star from formation to multiple explosions, it is necessary to solve equations describing hydrodynamics, thermodynamics, thermonuclear fusion, radiation transport, possibly magnetic fields, and rotation. These equations are nonlinear, interrelated, and span a huge range of scales. from the microscopic processes of nuclear reactions to the macroscopic motions of star-sized matter. Modern supercomputers allow for three-dimensional fluid dynamic simulations with unprecedented resolution. Researchers create models of stars with different initial masses, metallicities, rotation speeds, and trace their evolution to the final stages. Simulations show that the details of explosions are highly parameter dependent. Small changes in mass or composition can lead to qualitatively different results. More pulsations, less pulsations, complete destruction, direct collapse. One of the difficulties is taking into account multidimensional effects. Explosions are not spherically symmetrical. There may be convective motions in the star before the explosion, creating inhomogeneities. The shock wave can propagate unevenly. Rotation creates asymmetry. All this affects the observed characteristics. Therefore, modern simulations are increasingly conducted in 3 dimensions, taking into account rotation and magnetic fields. This is computationally expensive, but necessary to make realistic predictions. Comparing simulation results with observations is an iterative process. Models make predictions about light curves, spectra, and intervals between flashes. Observations test these predictions. If there are discrepancies, the models are refined. The physics of thermonuclear reactions, the equations of state of matter at extreme densities and temperatures, the mechanisms of radiation transport, all these components must be accurately calibrated. Sometimes gaps in our understanding are discovered, and new physical experiments or theoretical developments are required. For example, the equation of state of matter at densities close to nuclear densities is still not fully known. Under such conditions, nucleons begin to overlap, and the effects of the strong interaction appear, which are difficult to calculate from the first principles. Experimental data from high-energy physics and observations of neutron stars help limit the possible equations of state, but uncertainties remain. These uncertainties affect the predictions of supernova models, especially at the time of core collapse. Now let's move on to the question of how repeated supernovae can affect the habitability of planets and the galaxy. Supernovae are powerful sources of ionizing radiation and cosmic rays. If a supernova explodes close enough to a star system with planets, radiation can damage the planet's atmosphere, destroy the ozone layer, and sterilize the surface. Gamma rays and X-rays from a supernova can reach planets tens or even hundreds of light years away. A repeating supernova creates multiple waves of radiation. If a planetary system is in the affected area, it can be exposed to radiation again and again. This could have long-term consequences for the biosphere. On the other hand, supernovae also enrich the interstellar medium with heavy elements that are necessary for the formation of rocky planets and life. So it's a double-edged sword. Supernovae are both a threat and a blessing to life in the galaxy. For the Earth, fortunately, in the foreseeable future, there is no threat from nearby supernovae. The nearest known supernova candidate star, Betelgeuse, a red supergiant in the constellation Orion, is about 600 light-years away. If Betelgeuse were to explode, and it could at any time from tomorrow to 100,000 years from now, it would be a spectacular sight, visible even during the day, but not a danger to Earth at this distance. Betelgeuse is not a candidate for repeating supernovae. It is too massive for pair-unstable processes. It will explode once like a normal Type II supernova, leaving behind a neutron star or black hole. But imagine that in the past, the Earth could have been closer to supernovae. In the history of the solar system, 4.5 billion years later, there could have been events when nearby supernovae affected the Earth. There are hypotheses that some mass extinctions in the history of the Earth could be associated with supernovae. There is little direct evidence, but there are indirect indications. For example, the detection of isotopes of iron-60 in oceanic sediments several million years old. Iron-60 is a radioactive isotope that is practically not produced on Earth, but is synthesized in supernovae. Its presence may indicate that the Earth has passed through a cloud of matter from a relatively nearby supernova. Returning to physics, let's discuss the role of neutrinos in supernovae and repeating supernovae. Neutrinos are elementary particles that almost do not interact with matter. They are produced in huge quantities during the collapse of the star's core. When electrons are pressed into protons to form neutrons, each reaction produces neutrinos. In a few seconds of collapse, about 10 to the 58th power of neutrinos are emitted, carrying away about 99% of the energy of the explosion. Only about 1% of the energy goes into the kinetic energy of the ejected matter and the radiation we observe. Neutrinos from a supernova can be detected by detectors on Earth if the supernova is close enough. The most famous neutrino detection from a supernova occurred in 1987, when the supernova SN 1987A exploded in the Large Magellanic Cloud, a nearby galaxy about 168,000 light-years away. The Kamiokande detectors in Japan and the IMB detector in the United States detected several dozen neutrinos from this event. It was a triumph, the first direct detection of neutrinos from a supernova that confirmed the theory of nuclear collapse. For repeated supernovae, each explosion must produce its own batch of neutrinos. But paranstable pulsations work a little differently than core collapse. In a paranstable explosion, there is no neutron star formation, at least in the pulsation phase, so the mechanism of neutrino emission is different. Neutrinos can be produced in thermonuclear reactions, in the processes of annihilation of electron-positron pairs, and in other high-energy processes. Detailed calculations show that neutrino radiation in paranstable explosions can be significant, but less than in the collapse of the core. Detecting neutrinos from a repeating supernova would be incredibly valuable, providing direct information about the processes in the core of the star. Unfortunately, due to the rarity of such events and the need for them to occur close enough, the chances of detecting neutrinos from a repeating supernova in the foreseeable future are slim. But neutrino detectors are constantly improving, becoming larger and more sensitive. Maybe someday we will be lucky. Let's also talk about gravitational waves. Gravitational waves are ripples in space-time produced by the accelerated motion of massive objects. They were predicted by Einstein and first directly detected in 2015 by the LIGO detectors from the merger of two black holes. Since then, many events have been recorded: mergers of black holes, neutron stars, and combinations. Can supernovae produce gravitational waves? Yes, if the explosion is asymmetrical. A spherically symmetrical explosion does not produce gravitational waves because there is no net change in the quadrupole moment of mass. But real supernovae are not spherically symmetrical. Convection, rotation, magnetic fields all create asymmetries. When the core collapses and a neutron star forms, there may be fluctuations and instabilities that emit gravitational waves. For repeating paranstable supernovae, each pulsation can be asymmetrical, especially if the star is rotating or has magnetic fields. The shedding of the shell can occur unevenly. These are all potential sources of gravitational waves. However, the amplitude of the signal depends on the degree of asymmetry and the mass of the substance involved. Calculations show that gravitational waves from supernovae are weaker than those from mergers of compact objects, and it is difficult to detect them with existing detectors unless the supernova is very close. But future detectors, more sensitive or operating at different frequencies, could open a new window into the physics of supernovae via gravitational waves. It is also interesting to think about the relationship between repeated supernovae and the formation of elements. Supernovae are one of the main sources of heavy elements in the universe. During the explosion, fusion takes place under extreme conditions, creating elements as low as iron and nickel. Even heavier elements, such as gold, platinum, and uranium, are created in fast neutron capture processes called the R process. This occurs in environments with very high neutron density, such as neutron star mergers or certain types of supernovae. For paran-stable supernovae, each explosion synthesizes and ejects heavy elements. Multiple explosions mean multiple injections of these elements into the interstellar medium. If such stars were common in the early universe, they could quickly enrich the gas with heavy elements, accelerating the transition to the formation of second and third generation stars with higher metallicity. This is important for understanding the chemical evolution of galaxies and, ultimately, for the conditions that allowed planets and life to form. There is also the interesting question of whether repeating supernovae could be related to observed anomalies in the distribution of elements in some older stars. Astronomers have found stars with unusual chemical compositions showing an abundance of certain elements. Some of these anomalies are difficult to explain with standard models of stellar evolution and nucleosynthesis. It is possible that these stars formed from gas enriched in unusual types of supernovae, including paran-stable ones. Detailed modeling and comparison with observations can provide answers. Now let's talk about the cultural and philosophical significance of recurrent supernovae. The idea of a star that explodes and rises resonates with deep mythological and religious themes in human culture. A phoenix rising from the ashes, cycles of death and rebirth, eternal return. Recurring supernovae are the natural realization of these archetypes. They remind us that the universe is full of surprises, that our models and understandings are always incomplete, and that there are more mysteries behind each discovery. Scientifically, repeating supernovae challenge our understanding of the final stages of stellar evolution. They show that the death of a star is not always an instantaneous one-time event, but can be a long-term process with multiple dramatic episodes. They force us to rethink our ideas about what is possible in extreme conditions. There is also a practical aspect. Understanding repeating supernovae is important for interpreting astronomical observations. When telescopes detect a bright flare in a distant galaxy, astronomers must determine what the event is. A supernova? What type? Disposable or recurring? Further observational strategies, theoretical interpretations, and, in the case of the use of supernovae for cosmological measurements, the accuracy of determining distances and cosmological parameters depend on the correct classification. As we accumulate more data on repeating supernovae, we are starting to see that this is not a monolithic class of objects. There are variations. Some show 2 flashes, some more. Some have short intervals between flashes. Some are long. Some are bright, some are less bright. These variations reflect differences in the initial conditions, the mass of the star, composition, rotation, and the possible presence of a companion in a binary system. A systematic study of these variations will help us better understand the physical mechanisms. We will be able to build dependency diagrams, for example, how the interval between explosions depends on the mass of the star, or how the total energy released for all explosions correlates with the initial metallicity. Such diagrams are empirical laws that theoretical models are supposed to explain. They serve as tests for theory. Let us now imagine that we could observe a repeating supernova in real time with all the available means of modern astronomy. Automatic sky surveys detect the first flash. The alarm is sent to astronomers around the world. A massive observation campaign begins. Optical telescopes receive high-resolution spectra, track the light curve in different colors. Infrared telescopes look for signs of dust and molecules in the cooling substance. X-ray observatories monitor shock waves and hot gas, and radio telescopes track synchrotron radiation from relativistic electrons. Neutrino detectors stand in standby mode, hoping to catch at least a few particles. Gravitational wave detectors check the data for signals. The first flash peaks, then begins to dim. Astronomers publish quick messages, share data, and build preliminary models. Weeks and months pass. The object continues to dim, but not as quickly as expected for a normal supernova. Then there is a surprise. The brightness begins to rise again. The second flash. The observation campaign resumes with double intensity. The spectra of the second flash are compared with the first. Are there any differences? Has the composition changed? Speed? Everything is recorded and documented. Theorists, meanwhile, run simulations in an attempt to replicate the observed characteristics. What parameters of the star are needed to get two explosions with such an interval? Models are refined, compared with data, and adjusted. Perhaps it is necessary to include some physical process that was previously ignored. Science moves forward through an iteration of observations and theories. The third outbreak. Fourth, each adds new information. Gradually, a complete picture of the life and death of this amazing star is emerging. When it's all over, either the star finally collapses completely or stabilizes. We have an unprecedented set of data. This object becomes a cornerstone in the study of recurring supernovae, a benchmark against which all subsequent observations and models are compared. Of course, the reality is more complicated. Weather can interfere with observations. Telescopes may be busy with other programs. Funding may be limited. But even with these limitations, every new discovery of a recurring supernova is an opportunity for science. And with each new object, we understand a little more. As we wrap up this journey through the world of recurring supernovae, let's go back to the beginning. Zombie stars. Stars that explode and resurrect. This is not just a beautiful metaphor. These are real objects that exist in the universe, demonstrating physics at the limit of extremes. They challenge our understanding, force us to rethink what we thought we knew. They remind us that space is not a static place described in textbooks. It's a dynamic, ever-changing arena where incredible things happen, where stars are not just born, live, and die, but sometimes go through the agony of repeated explosions, each of which can outshine a galaxy. They also remind us of the fragility and preciousness of our existence. We are the products of stellar evolution. The atoms in our bodies were formed in the bowels of stars and scattered across space by supernova explosions. Without supernovae, there would be no heavy elements, there would be no planets, and there would be no life. We are literally stardust, collected in complex structures capable of cognizing the universe. And here we are, standing on this small planet orbiting an ordinary star in the outskirts of an unremarkable galaxy, looking up at the night sky, and we see flashes of light that have traveled millions or billions of years to reach us. And we can analyze this light, extract information from it, build models, and understand processes that occur at unimaginable distances. Repeated supernovae are another chapter in this great history of knowledge, a chapter that is just beginning. With each new telescope, with each new survey, with each new discovery, we learn more. And who knows what other surprises the universe has in store for us. Maybe there are even more extreme objects that we haven't discovered yet. Maybe there are stars that explode dozens of times. Maybe there are mechanisms that we don't even know about. The universe is full of mysteries, and our task as a human civilization is to continue to explore, to continue to ask questions, to continue to search for answers. Repeating supernovae are not just an astronomical phenomenon. This is a window into fundamental physics, into extreme conditions that cannot be reproduced on Earth. It is a laboratory of nature where our theories of gravity, thermodynamics, nuclear physics, and quantum mechanics are tested. They are also of practical importance. Understanding how stars evolve and explode helps us understand the history of the universe, the formation of galaxies, the enrichment of the interstellar medium with heavy elements, and the conditions for planet formation and life. And on a deeper level, studying recurring supernovae is part of our quest to understand our place in the cosmos. Where did we come from? How did the universe come into being as we know it? What is our fate? These eternal questions drive science, drive research, drive human curiosity. So the next time you hear about a supernova discovered in a distant galaxy, remember that this may not be the end of the story. Could be a zombie star preparing for the next act of his space drama. And somewhere astronomers are watching it, recording data, building models, trying to unravel its secrets. The universe is amazing. The universe is full of wonders, and repeating supernovae are one of the most exciting wonders we've discovered. Stars that refuse to die, astronomers' nightmare and their greatest reward. Because every anomaly, every inexplicable phenomenon is an invitation to learn more, to dig deeper, to expand the boundaries of our understanding. And this is the whole essence of science. Not to have all the answers, but to keep asking questions. Not to know everything, but to admit that there is still a lot we don't know, and to be willing to be surprised, to learn, to grow. The recurring supernovae surprised us. They showed that the universe is stranger and more beautiful than we could have imagined. And this is just the beginning. There are more discoveries ahead, more surprises, more reasons to look at the sky with awe and delight. So keep looking up, keep asking questions, and remember, somewhere out there, in the depths of space, a zombie star is preparing for its next explosion. And when this happens, we will observe, learn, and be amazed. Because that's what makes us human. This is what makes us explorers of the universe.